All right. So this first one, this is a Gallup poll released in December 2010, asked 1,019 adults living in the continental United States about their beliefs in the origin of humans. These results, along with the results from a more comprehensive poll from 2001, we will assume to be exactly accurate. So this is the expected. This is the expected. This is the observed. Right? We're assuming 2001 is accurate. This is expected. And then this is going to be observed. We summarize the table below. Okay, state the hypothesis for the following research question. Have beliefs on the origin of human life changed? So we're saying so when we say the population, we're saying the 2010 population, does it follow 2001 or not? So we assume it follows it unless proven otherwise. So you're good. This is going to be the second choice. So now we've surveyed 1,019 adults. So if they're the same, right? If we're going with the null, we're assuming the null is true, then the statistics from 2001 should hold. So I'm just going to multiply my sample size by each of these percentages to find the values I would expect and the values I actually observed for each of the different belief categories. So it says round to the nearest whole number. Sure, we'll do that. So let's do the observed 2010. That's more straightforward, I think. 2000 or 1019 times 0.38. So 387 people we observed. Said that humans evolved with God guiding. We'll do the same thing with 16%, 163. And the last two, 40 and 6. Okay. 408 and 6%. 61. Right now we'll do, okay, if they were the same, if the distributions for 2001 and 2010 were the same, we would expect these percentages to hold. So now I'll just multiply by these numbers to get my new expected times 0.37. We'll do times 0.12. 377, 122. So this is 377, 122, 45 and 6. $459 and 61. Okay. So now we're going to conduct the chi-square test and state your conclusion. So really, if you get confused as to which test to run, there's kind of like a cheap way to figure it out. If you go over to tests, you really only have two options. They're both chi-square tests. But we want the one that involves the lists because we have a list of something observed in 2010 and something observed in 2001. So if you just click one, let's just say chi-square goodness of fit. Oh, look, this is the one that takes tests. It's the other one that takes matrices. So I'm going to use the goodness of fit test. But before I use that, I have to go in and put my data into my stat list. So my observed will be in L1. And my expected will be, double check, make sure everything's entered correctly. My expected will be in L2. Stat test, chi-square goodness of fit test, observed L1, expected L2. Degrees of freedom, when you're conducting these tests, the degrees of freedom is going to be the number of categories minus 1, 4 categories. So we'll have 3 degrees of freedom. And we get all of our good stuff. So it says the value of the test statistic is 19.71. The degrees of freedom we just said was 3. The p-value for this test is 1.948. Don't forget that e to the negative 4. So that's 3 zeros and then 194. So this would be 0.0002 to 4 decimal places. Normally it would be 0.00019, but we rounded 4 decimal places, we get 0.0002. So this is really small. So P is going to be less than alpha. So if P is low, we reject HO. So HO says the population follows the 2001 distribution. So we could say the data provides sufficient evidence to claim that the 2010 distribution is different than the distribution in 2001. There you go. All right. Rock, paper, scissors, yada, yada, yada. We know what rock, paper, scissors is. It says use these data to evaluate whether players choose between the 3 options randomly or if certain options are favored above others. So if they choose them randomly, it might seem a little weird, but if they choose them randomly, we would expect rock, paper, and scissors to show up the exact same amount of times. All right. So how many people did they check? Let's just add these values together. 99. So if they were truly random, we would expect 33 people to throw rock, 33 to throw paper, and 33 to throw scissors. So we're trying to say they're all the same unless we can prove otherwise. So it's a weird way to say it, but they're uniform. They're all the same. We're trying to show that they're not uniform. Okay, we're not singling out a particular throw. And we are assuming that they're the same. Use this data to evaluate whether players choose between these options randomly or if certain options are favored. So we're not going to assume that the observation is the truth. We're going to assume that they're equal and use the observation to prove otherwise. So this is kind of like flip. These should all be 0.33. So your answer is going to be the second one. All right. So we're comparing two things, observed and expected. So it doesn't seem like it because of the way I wrote it. But this is going to be a L1, L2 thing. So let's clear this out. So I have observed 43 rock, 21 paper, 35 scissors. I expect even number. So expected is L2, observed is L1. Stat, chi-square goodness of fit test, observed is L1, expected is L2. Degrees of freedom, we have 3 categories here, so this is now going to be 2. And we calculate. Test statistic is 7.52. Degrees of freedom, we just said were 2. The p-value associated with it is 0.0233. Do they give us an alpha value? I don't believe so. But alpha is usually 0.05. So we'll say here p is less than alpha. Reject HO. So now we go back and revisit what our HO was. The distribution is uniform. So we're now rejecting that and accepting the alternative. So it says the data provides sufficient evidence to claim that rock, paper, and scissors are not chosen equally as often as one another. Yep, that's what we were trying to show and did show. Okay. And the last one, it says diabetes and unemployment. A 2012 Gallup poll surveyed Americans about their employment status and whether or not they have diabetes. The survey results indicate that 1.5% of the 47,774 employed, full or part-time, and 2.5% of the 5,855 unemployed have diabetes. So I have to use that information to fill in this chart. So 1.5% of the employed people have diabetes. So we'll take the number of employed times 0.015. So that many people that are employed have diabetes. So this is, does it say to the nearest one? We'll just do 1 decimal place. Maybe we need to. No, let's keep it as whole numbers. Uh, 717. No, you know what? I want to make it a little bit more accurate. It doesn't specify, so I'm going to do 716.6. One decimal place is fine. Okay, which means the rest. Well, scratch that because we're dealing with people. I don't want to avoid. I want to avoid decimals. 717, which means the rest of those unemployed people. These people are not sufferers of diabetes. So 47774 minus. If you use the decimals or not, it's not going to change your answer because our numbers are so large. So it doesn't really matter. It's a personal preference. 47,057. Okay, and then 2.5% of these group, the unemployed, have diabetes. So we'll do 5,855 times 0.025. So we get 146. Subtract to get the people who don't have diabetes, 5,855 minus 146, 5709. Okay, that's our matrix. We're trying to see if there's a relationship between the columns and the rows. So I'm going to input that information into a matrix. If you go to your matrix and you have something in there, there's a couple ways you can clear it. I just like to clear the calculator every single time. So I do second plus 712. Now I'm going to edit. I have a 2x2 matrix. So I'm going to fill in the numbers, 471. Okay, so state the appropriate hypotheses to test for independence of incident of diabetes and unemployment. So basically, you're just seeing if these two things, these two measurements are related. So let's see here. The average of diabetes is equal to the average of unemployment. I don't think so. Diabetes status and unemployment are independent. And we're trying to show the opposite. Diabetes status and unemployment are not independent. So that's the one we're going to go with. We always assume independence and then try and show the alternative. So we're not going to use this. Right? You can't really assume dependence. That's poor math. So we always assume independence and then try and prove otherwise. So let's run the test. That's all good. Clear. So we'll go stat test. Now we're just running a chi-squared test. Observed is A, so yada, yada, yada. Okay. The sample difference is about 1%. If we complete the hypothesis test, we will find that the p-value is very small. Yep, we have 7 zeros and then a 1. So it's basically 0, meaning the difference is statistically significant. Use this result to explain the difference between statistically significant and practically significant. Just because something is significant by mathematical standards, it doesn't necessarily mean it's significant in the real world. This question is not going to come up on the problem set or quiz. But generally speaking, since the number of the size of the sample is so large, and we're talking about fractions of percents, that it's not practically significant, even though it may be significant when referred to statistics specifically. So let's see here. Since the sample size is so large, the difference between two samples proportion is so small. Yeah, it's not necessarily practically significant. Okay. But again, I wouldn't waste any time on this one.